Now, you might go to the restaurant, if you remember going to the restaurant, and you might have a delicious meal with a delicious drink and some ice cream after. And at the end of the meal, you might have to split the check somehow. And so we're going to go ahead and we're going to split the pressures of a sample of gas and use something we call partial pressures. And the way we're going to do it, if you imagine that this is air, and air is about 78% nitrogen, so N2, that's a diatomic, and that's a gas. It's about 21% oxygen, which is, for us, the most important thing probably, and this is dry air, by the way, and it is 1% argon, so that's that noble gas there. That's surprising, there's so much of the air that's argon, actually. And the way we do it is we say that the total pressure of the air itself is equal to the partial pressures. So we assign each gas its own pressure, and so we use P for pressure, and as a little subscript we write the gas down there. So this is actually called Dalton's law of partial pressures. And in general, this is kind of how we split the check here. So we say that the total pressure is equal to a bunch of part pressures or partial pressures that we can add together to get the total pressure. And if you're like, well, how does that help us find the partial pressures? So how do we know what all of these are? Well, it turns out that we can just take the percentage of each gas. So if the nitrogen is 78%, that is 78 over 100. And we can multiply that by the total pressure. So this is the fraction of each gas, so okay, and we multiply that by the total pressure. So we normally know the total pressure, and so we just want to assign the partial pressures in the same way we might know the total bill at a restaurant, and we might want to assign the parts of the bill that we're each responsible for. And so the air pressure itself, we said, is 760 millimeters of mercury, and so we can calculate now the partial pressure of nitrogen by just taking the fraction that's nitrogen and multiplying by the total pressure. And if we pop that on our calculator, I get something on the order of 590 millimeters of mercury, or torr if you prefer. We can do the same thing for oxygen as well. So the oxygen, it represents 21% of what we're breathing in, so 21% times by 760. So this is very fair, right? So we're saying if 21% of the air is oxygen, it gets 21% of the pressure. And so if we go ahead and we calculate that, I get 160 millimeters of mercury. And we can do the same thing for the argon. So if we do the argon in green, it is 1%, so that's 1 over 100 times by 760 millimeters of mercury. And that's something like 7.6 millimeters of mercury. And if we add all those up, if we add together the 7.6 with the 160 from the oxygen with the 590 from the nitrogen, we should get something very close to the total pressure, 760 millimeters of mercury. So that makes sense. It should all add up. So when you go ahead and you split the bill at the restaurant, all the individual portions should add up to the total amount. Now, with rounding, I think it probably doesn't come out quite exactly right with this problem here, but it should be extremely close. So we can use an application of partial pressures, of Dalton laws of partial pressures. If we remember, the pressure of air is the partial pressure of nitrogen and oxygen and argon and carbon dioxide and whatever else it may be. And we know that each one of these partial pressures must add up to the total pressure. Well, if the total pressure is actually a little bit lower, that means all the partial pressures have to be lower. So if you were sitting on top of a mountain here, somewhere in North America, and okay, we can draw ourselves here. We're pretty good. We're up pretty high. And it turns out that air, right, pushing down on you is what's given rise to air pressure. And the thing about climbing up a mountain is that when you climb up a mountain, there's less air above you. And so the total pressure is much smaller when you're up the top of a mountain. So if the total pressure is smaller, that means the total pressure of air is smaller. So it means that all these partial pressures have to be smaller too. So why do we care about this? Well, if your total pressure is smaller, that means that all your individual partial pressures have to be smaller, and that means that the pressure, or the partial pressure of oxygen, has to be smaller. So at the top of a mountain, you might have more trouble breathing because there's literally less pressure of oxygen in the air. And so if you train, say, at high altitude, altitude, your body gets used to this lower pressure of oxygen, and it normally compensates by making more red blood cells. And then once you're used to it, after a couple of weeks, you come down the mountain and you compete in the Southern Ohio Olympics, let's say, if that's such a thing. And you've got all that extra blood that's capable of carrying and grabbing all that extra oxygen out of the air. And so at least for a week or so, you do a lot better than you should be.